Okay, so before I start, the disclaimer. I've never taught meta-complexity before. I've given very few talks on meta-complexity. Most of the slides have been written very recently, and chances are they're very buggy. So please, if you notice mistakes, point them out so that I can fix them. And another disclaimer is that there are people in the audience who have known the subject way better than me. And I might redirect some questions, and please tell me if I'm saying something that's iffy. Okay, meta-complexity. So, for something completely different, what's meta-complexity? Where does meta come from? Complexity, we are trying to characterize the hardness of a computational problem based on the number of resources it requires. Meta-complexity, we are trying to figure out how hard it is to determine, given a problem, the amount of resources it requires. Meta-complexity connects to all sorts of things throughout complexity, and more stuff comes up in just the last, I think, 5 years, 10 years. There was a lot of progress, and I will try to sketch at least some of the things, some of the connections, and some of what is known about meta-complexity. The obligatory showing pictures and asking you which one you think is more complex, just to define what meant by complexity. I mean, I will be defining it and defining it and defining it again in all sorts of different ways, because there are many different ways of defining complexity, and they do behave often quite a bit differently. So, okay, which string is more complex? Which picture is more complex? Yeah. So the first picture. Wait, I think you've heard it before and you've seen it before from other speakers. Random noise, hard to describe, no rule or rhyme or reason or structure, versus something that has a lot of structure and a lot of a lot of patterns inside it. And just to say that complexity, meta-complexity, is very crucially related to learning, because really what both meta-complexity and learning are, you're trying to figure out the patterns in the world around you. The world around us is not quite random noise. At least I'm seeing some more structure in this room than just white dots on gray background. And also it's related to pseudo-randomness that Amir already talked about and introduced very nicely. It's about distinguishing whether something is random, or if there is a pattern but the pattern is hidden, or if there is a pattern but it's so well hidden that you really need to do a lot of work to figure out it's there. Okay. Do you want to see more binary strings? Okay. Just kind of to run through some running example. A lot of time I will be going back and forth between two views of binary strings at the powers of 2. One of the views is, well, it's a binary string of length n and happens to be power of 2, but whatever. Another view is oftentimes when you look at a string of length 2 to the n for some n, you could view it as a truth table of some Boolean function on log n variables. And this view is very, comes up a lot in a lot of meta-complexity questions. So even though some of the many of the definitions, they don't really require this approach. This is one thing that will come up over and over. So if you see a string of length 2 to the n, one way of thinking about it would be, oh, it describes a truth table of a Boolean function, and how hard is this function to compute. So for example, the first string, if I did it right, describes basically a truth table which the function is just the value of the last variable. The next one is one of the favorite ones in complexity. I've heard Ryan Williams once say, if you think you've proven something big, try it on parity on XOR SAT. It's like one of the first things to try when you want to see if your approach works. So second one, if I wrote it down correctly, is you have your input and you want to know whether parity of the input bits is even or odd. This is the cool one because it's super sensitive. We know cool lower bounds for it. We know very, very strong lower bounds for it in lower complexity classes. And it keeps coming up a lot in all sorts of settings. And the last one, I don't know whether it's how random it is. I just randomly put in zeros and ones, and hopefully it's random. So one thing to say about meta-complexity, it's a zoo. It's a real zoo. There are lots of complexity measures that are kind of related, sometimes just morally related. A lot of time things are proven for one and similar things are proven for another, sometimes not. There isn't really much of if this measures and this measure kind of results. It's a bit of a zoo. So what kind of measures in particular I will try to talk about. So I'll start with a very dilettante mentioning on a few things of Kolmogorov complexity, and apologies to experts in the audience. Then I will talk about several ways of scaling down Kolmogorov complexity to computational complexity realm, sort of computability to complexity jump. There are multiple ways of doing it which give you pretty different measures. And also, I'll talk about coming up with a measure more from complexity side directly, which is size of the smallest circuit, sometimes a circuit of certain type that computes a given Boolean function given as a truth table. So I will probably mostly talk about the plain versions of all of them. There are lots and lots of subtleties about maybe rather than computing a measure, you want to distinguish between having this measure being small versus being big. And some of the results we kind of know just in this setting. Sometimes we talk about, a lot of times we talk about what it means to compute and what it means to prove hardness, because interestingly enough, there is a lot of barrier results here. You cannot prove certain things certain ways. I think some things you cannot prove with respect to oracles, relativizing. Some things you cannot prove in a black box fashion. If you talk about a program, you really need the code of the program to make your result go through. Lots and lots of things like that are going on, and I'll try to mention a few of those. Barriers are fun. But probably even more interesting to at least in view of what's been happening in the last few years, is how much meta-complexity interacts with the rest of complexity theory, at least. I already said that meta-complexity kind of morally pretty similar to learning. In learning, you are trying to figure out a small description of the world you are seeing. In meta-complexity, you are trying to figure out if there is a small, well, description of the world that you are seeing, where your notion of description and small varies widely depending on which part of the zoo you are. Recently, in the last 5 years, there were really cool connections with cryptography. In particular, kind of meta-complexity is now almost seen as a way towards the holy grail of trying to make cryptography that's based on NP hardness. We are not there yet, but there have been cool results that relate existence of cryptographic primitive, in particular one-way functions, to hardness of meta-complexity problems. Hardness oftentimes is, especially in cryptographic setting, not the worst case hardness as we are used to, but more average case hardness. Again, maybe some of you are more used to average case hardness, typical complexity, but there are different ways of defining average case hardness, and they seem to make a huge difference in what we could prove. The hardness that you need to relate one-way function to a meta-complexity problem is defined slightly differently from the hardness that you need to prove that for some meta-complexity problem, if you could solve them well on average, you could also solve them well in the worst case. And again, I'll try to talk about it, but things get kind of subtle. Small change to definition can really change your problem in this field. And I will try to mention some connection to proof complexity, probably not as much as I would like to, but one of the very natural meta-complexity questions is when your computational object is not a kind of a machine or a circuit computing a function, but your kind of computational object is a certain proof system. And I will try to say at least a few words about connections between some notions of meta-complexity, some of the things in the zoo, and some notions in proof complexity, particular proof search. So any questions, comments so far? Chances are I won't have a chance to go deep into anything. I'll give a few simple reduction and I'll try to wave my hand about constructions. But I'll try to point you to the places where things were proved so that you get the general lay of the land, and you could then go and look deeper into things that kind of were curious to you. Wait, did I? Okay, so, and another thing to say. Over the last several years, meta-complexity has become big, and so there were a lot of workshops in schools on meta-complexity. And in particular, a big thing was Simon's Institute program on meta-complexity 2 years ago that some of you have been to. It was fun, mainly because you've been there. And there are lots of very good videos about meta-complexity from there, especially from the bootcamp workshop where the whole week there were tutorials on different parts of meta-complexity. And what I will try to do, I will try not to repeat things that other people went in depth, but more kind of sketch a few little things that other talks tend to take for granted. And I remember myself wondering, oh, wait a moment, like, why is this true? But the videos on bootcamp, and Eric Allender gave a great public lecture there on meta-complexity. Pretty much every time you Google on YouTube for name of the talk that says something about distinguishing complex from random, order from chaos, and combination. Chances are it will be a recent meta-complexity talk. A year ago, there was a workshop here on complexity, which, among others, had Igor Oliveira and Valentin Kamenets talking about on things that are pretty much meta-complexity, at least in my view, or very much related to meta-complexity. So, in particular, Igor gave a survey on probabilistic notions of meta-complexity. Chances are I won't touch it, but he has a survey on it, and his talks are great. And Valentin Kamenets was talking about a lot of learning pseudorandomness, meta-complexity connections. Another resource is last year there was a graduate research school last summer at DIMAX at Rutgers. Again, probably some of you have been there, and Rahul Ilanga gave an excellent long tutorial on meta-complexity. I will probably try to stay away from things that he emphasized, just to give you a little bit more breadth. In particular, he talked a lot about connections with that average case complexity. So that would be a great place to check if this is the part of meta-complexity you're interested in. And just a month ago, well, 2 months now, we had a workshop in San Diego on connections between meta-complexity learning and cryptography, and there were also some tutorials there. And there are surveys. Eric calendars are probably the most standard, but Igor Oliveira wrote surveys, and I'm pretty sure I'm missing people. And if you Google for courses on meta-complexity, there are a few. So Niall taught a course on meta-complexity, Marco Carmazina taught a course, probably Igor taught a course as well. There are resources. Very recent, but there are resources. Okay, any questions or comments so far? And by the way, I'm open to suggestions and discussion. If you really want to see something, please tell me, and I'll try to figure out by tomorrow. Okay. So let me talk a little bit about some definitions. So first of all, with apologies to Kolmogorov complexity experts in the audience, probably the first measure that really was trying to capture what does it mean for a string to be random, for a string to be complex, was Kolmogorov definition. So a lot of time when people talk about randomness, they think about randomness in the way that Amir talked about it. You talked about distribution, you talk about information with respect to distribution. Kolmogorov's approach, as I understand it, was starting with, if you just look at individual string, how much really kind of information or randomness is in that particular string independently of where it came from. So like those two strings, probability of picking them uniformly at random is the same, but you'd all agree that they do look to have different complexity. And in a line of work in the 60s of Kolmogorov, as well as independently Solomonov and Chaitin, they came to a notion that roughly says something like that. Let's define the complexity of a string to be the length of the minimum length of a description of the string, from which you could then recover the whole thing. And there are several ways of defining it, and I'm going to be grossly abusing the notation and conflating things that really should not be conflated, but just to give you an intuition. So one way of talking about what the minimal description is just to say, I want to pair a Turing machine and a string, and I want my complexity to be the smallest size of that pair, such that on input on input string, the machine generates whatever string you want. So for example, the string 010101 can be generated by a machine that takes as an input number of times it needs to output 01. Every string can be generated in the time length of the string itself, plus a constant. The constant you could, again, with apologies, very loosely think of as describing whatever else goes in the description of the machine, like the print statement and other stuff. So, and another definition is you just fix a universal machine, and you just say it takes strings, descriptions. And we won't really be too picky about what those descriptions look like, kind of machines. And that's another kind of way of doing things. In meta complexity, I don't think it matters that much. So one big thing that probably makes Kolmogorov complexity people here cringe is that I'm using the letter K of X to mean Kolmogorov complexity when I define it the way I did. I know I should be using C, but because the K is reserved for a special kind of language, which is a prefix-free code where you don't need to say how long your string is. It's self-delimiting. If you read pretty much any survey of Kolmogorov complexity or hear a talk, they will say the same thing as I'm saying. Now, I'm going to use K just because it's our convention, and other things will have K in it when I define it later. But yeah, I kind of know I should have said C. So good things about Kolmogorov complexity is that really, if you take any kind of reasonable description language, then the difference between lengths of vast majority of strings will be just a constant factor. So it's a very robust definition. It really doesn't matter whether you want Turing machines or a Python code or, I don't know, Java code, which tends to be quite a bit bulkier. It's still roughly to a constant would be similar. Okay, so yeah, invariant theorem is just a theorem that basically says, you know, don't get too hung up on how exactly you define a universal Turing machine, just pick a good one and that should do. Another thing is a relation between randomness and compressibility. So Kolmogorov defined a random string, or to be just incompressible string. You could show by just a counting argument that there is a string of lengths for every n. There is a string that you cannot compress to less than n just because there are not enough descriptions. Every description corresponds to one string. Well, there are 2 to the n strings of length n. Some of them you cannot describe shorter. So a random string would be the one which kind of has maximum description. And again, there is a little bit of flexibility with how much away from the maximal length you really want to, maximal -1, maximum minus a small constant. I am sweeping this under the rug. All I want to say is for all of those definitions of randomness, at least half And for more relaxed one, vast majority of strings would be random. You pick a random string, it would be, well, incompressible. So that's kind of the connection. Any questions, comments, mistakes on the slide that I definitely should correct? So yeah, this is what I was just saying. There are lots and lots of strings that the further you go away from having the length of the string as your minimum description length, you know you could always do it length of the string plus a constant, but vast majority of strings you need length of string minus a constant size. Questions, comments, suggestions? Yeah, what I didn't want to say about it. So one interesting thing with a lot of proofs that you see in meta complexity is a lot of time, with a few notable exceptions, you are really talking about distinguishing simple from random, and the random is really random. Recently, people started talking more about what they call computation depth, namely difference between Kolmogorov complexity of a string and a computational version, as in there is a small description, but it's really hard to compute. But for a lot of proofs, really, oftentimes, it just distinguishing truly complicated strings, time-bound doesn't matter, from strings that not only have small description, but this description is easy. Okay, questions? Okay, so one of the things that was kind of, I think I've heard from somebody, I think it was attributed to Kolmogorov. Enrico Fermi asked, why can't we find aliens? Are we the only people in the universe? And to which Kolmogorov said, well, you know, if aliens are smart, and we assume they're smart, then they're probably communicating in a very efficient way. That means that their messages are pretty compressed. That means you can't really tell them from random noise. So, okay. So Kolmogorov complexity is a great notion. It has one disadvantage in that it's undecidable to determine it. And before I show you the standard proof of it, let me tell you kind of Russell's version of the intuition of the proof. If you ever teach discrete math, that's a fun one to do. So here is, I claim that there are no boring integers, no boring natural numbers. Why? Suppose I take the set of all boring natural numbers. By well-ordering principle, there will be the smallest one by the absolute value. That's a pretty cool number, right? You know, this is the smallest boring number. To me, it makes it not boring. Well, therefore, the set must be empty. So this is very similar intuition to me why Kolmogorov complexity is uncomputable, because if you can pinpoint it, that pointer, you could set things up so that it's shorter than the complexity that you alleged. So more precisely, here is kind of a sketch. So suppose there is a machine that's compute the Kolmogorov complexity, and let's just, for simplicity, say there is a large constant involved, so we don't need to deal with small numbers. The machine will work like this. It gets an input in binary, and then it looks through all the first however many descriptions until it finds one of Kolmogorov complexity significantly greater than k. Well, eventually it will come up with one because for any input run, you fix the k, you fix the c, there are infinitely many descriptions, their sizes increasing, eventually you'll hit the one. But in this case, this machine M together with the number k is a shorter description length, k is given in binary, than what you assumed Kolmogorov complexity of Si is. So this is a contradiction, and so no Kolmogorov strings are boring. Well, I don't know. Questions, comments? Okay. So far, we talked about Kolmogorov complexity, a very nice but not very computable notion. And naturally, there were attempts by people to scale it down from computability to complexity. I guess in the 60s, 70s, 80s, there was a big grand plan of taking things in computability, scaling them down to complexity, and seeing what we could prove. At the beginning, things work well, and then people start running into barriers. But at least Levin kind of took Kolmogorov complexity down to computational complexity realm. And he defines the following notion of the time-bounded version. So now not only you want the smallest description, but also you include as part of your description the logarithm of the time it takes to print the thing. Notice that why logarithm? Some versions won't have logarithm, but Levin's version had logarithm for a very intuitive reason. You need time t to just print the string. No matter how easy it is, if you're printing it, you're spending t steps. So my understanding is the reason he had it as log t was to try to really emphasize, can you find the string easier than some kind of big brute force search over something? Or, and not really have the length of the time you need to print it be like a major part of your thing. So generally, if you have like negligible size description, some very small constant, you could print your string in time, that constant plus log of the number. And also, on the other hand, if your description is a string itself, you could print it out. Your KT complexity would be length of the string plus log of the length of the string to print it, plus a constant for your print statements. Okay, questions, comments? So what can you do with this definition? Levin did a very interesting thing. What he did with his definition was to define a universal search. So here is an idea. Okay, so say now your setting is you have some function, and we'll talk more about it later. Let's even say easily computable function f of, that maps x's to y's. Somebody gives you y, promises that there is an x such that f of x is equal to y. You want to find x. So how can you find it? You could start by saying, well, maybe my y is very simple. Let me see if my very first Turing machine describing the simplest string will print it. Well, no, well, okay, let me try the next one. So crucially here, you go through your potential descriptions of that string x that gave you y in the order of KT complexity. And every time you have certain KT complexity, you kind of break it down into the length of the machine and log of the running time. And so you run that machine for that much time. And what he showed is it's actually a very efficient way of finding things. You can figure it out kind of in the time optimal to a constant. It's really cool. Questions? With this definition, you can kind of already see how it will relate to cryptography. Because, yeah.
Where is F in the universal set? Or is that different?
Check if it outputted x such that f of x is equal to y.
Oh, okay, I missed that.
Yeah.
What do you mean with optimal?
Well,
Meaning as a machine for time-bound model complexity?
it's an optimal way to, generically, if you want to be able to do the search no matter what f somebody gives you, this is an optimal way to be searching for the x's. Yeah. So it's optimal as a way to find an x given y. Very, very generically.
So the complexity of F should also appear in the description.
I think I did mention that, let's say f is polytime computable, so it's like, okay, it's this thing times the amount of time you need to compute x, f of x. Yeah. But this is a verification part. Yes. Yeah. Very good point. All of it is multiplied by the complexity of f. So really, you don't even need f to be like certain time class. It's just you multiply by the complexity of computing f of x. Yes. Very good. More points. Great. So you, with this, you can kind of already see where it will later, in a much more complex way, and not quite for this notion of complexity, connect to cryptography. Because if you have a function that you're assuming is one-way function, so it's hard to invert, well, you know, you could still do the universal search. Okay, so now let me digress, and this is kind of a little bit, okay, proof complexity. Raise your hand if you've seen a proof system. Like, raise your hand if you've seen truth tables. Okay, truth table is still a proof system. It lets you take any tautology, propositional tautology, and figure out if it's true on all possible assignments. Generally, the definition, Cook and Rackhouse definition of a proof system is a function that takes a proof and checks it and maps it to a tautology that is proving. And the proof system is automatable, used to be called automatizable, if there is an algorithm that inverts this function. So there is a function that maps proof to tautology. I give you a tautology and ask you, give me a proof in such and such proof system. If I ask you for a truth table, sure, you could do it. In time, which is polynomial in the length of the smallest truth table, well, truth table of time 2 to the n times the size of the formula, yeah, you could do it. But if you get some proof system which is a little bit more interesting, like a resolution proof system, then the question of whether those systems are automatable have been around for a while and only recently been solved. So In order to talk about it from meta-complexity perspective, let's define conditional Kolmogorov complexity or conditional KT complexity. It's kind of, from what I understand, generally you could do conditional more or less the same way with those measures. You say now the machine that's supposed to get a description D and print out X in time T, it also gets another string W. And here I am kind of assuming sweeping under the rug that you probably want some kind of random access to the string W or oracle access or something like that. So if your W is gigantic, you don't have to actually spend time reading all of W, and that would mess it up. How it comes in proof complexity? Well, you're proving a tautology. So you kind of want to know the length of the proof given a tautology, right? And this notion, KT, of a proof given a tautology is the one that comes up. So just recently, Jan Krajcek defined kind of the, did he call it, the information contained in a proof as exactly this, this notion, the complexity or KT complexity of the proof given the alleged tautology, the formula. And he shows that the proof system is automatable, that is, you could find proof if and only if for every, how do I, if the minimum over proofs of given tautology, because you can always go off on a tangent, proofs of a tautology in the system is bounded by the logarithm of the size of the proof in the system. So this gives you kind of a direct connection between meta-complexity notion, KT, and the very kind of, I would even say, practical task of searching for proofs. Interestingly enough, also very, very recently, several people have shown, for Atzerius and Miller, shown that for the resolution, probably the most common proof system, it's actually NP-hard to find the smallest proof, even if you know it exists. Or another way of saying what they show is that NP-hard to distinguish between having a small proof or every proof being gigantic. And in more recent work, this has been extended to other proof systems. Questions, comments? Okay. So KT seems nice. What do we know about computing it? So let's define MKTP problem, MK little t p problem, minimum KT problem, as follows. I give you a string, I give you a parameter in binary, and I ask you whether Levin's KT complexity is at most this parameter. Well, so this is a very, well, this is a very interesting question. On one hand, it's kind of decidable, because now you could brute force over, you have your parameter. You could brute force over the description plus time up to this. So in exponential time, you should be able to figure it out. On the other hand, very natural question, is it actually complete for exponential time? Sounds like it should be. Here, the things become very murky. Because yes, there is a proof that it's kind of sort of complete for exponential time, but in order to compute the reduction, you need the machinery that's not really the one that we usually associate with completeness reductions. So rather than having like polynomial time, exponential time functions computing, you know, you take some exponential time complete problem, maybe succinct circuit evaluation, and then you try to reduce it to min KTP. In order to be able to do this thing, you seem to need not machines computing your functions, but non-uniform circuit family. And moreover, it's not like you just apply the function, you stick in your instance of your X-complete problem, out comes the instance of MKTP. It's more like you need Oracle access. You need to be able to ask many MKTP questions in order to solve the original problem. It's surprisingly complicated. And it's still not clear whether it is possible to do under normal reduction. And it's actually still not clear whether you could figure whether computing MKTP can be done in polynomial time. Very weird. Questions, comments?
This question is open formally in the same sense that we cannot prove whether P is equal to NP, or you really have doubt whether it's computing polynomial time or not?
I think my take on it is it open in the same sense as, you know, NP is not equal exponential time. We kind of do believe it, but we have no idea how to actually prove it. And that would require something, something different from what we usually do. There are lots of those barriers to what kind of reductions work for what kind of problems in this area.
But can you comment more about like in what sense it's complete? Like, if I cannot do the polynomial time, it would be like the X.
You know what? I'm thinking, should I skip over to like? I do have slides on it later on. So it's so. Yeah. Sorry, say it again. Yeah, I think so, yeah. Yeah, but we don't know it, right? We don't believe it, but we don't know it. Yes, yes, very good point. It would imply that X isn't poly, which would make a lot of things very different, yeah.
I guess the point is that there's hope. The point you're making is that there's actually hope we could prove that it isn't, but we don't know because the reductions that we know are non-uniform.
Yes, exactly. Yes, thank you. That's a much better way of saying it. So, yes. Sorry, did this answer your question? Yeah. It's one of those complexity statements. Embarrassingly, we don't even know that this kind of very blatant statement is not true. Is that good interpretation? Yeah. If X isn't poly, lots of things become really weird. And under what kind of reductions? Under Okay.
I could be misremembering that.
There could very well be this result, and I'm just not remembering it. There are results like that for different definition of MKTP under different reduction, but this is a different, this is not the paper you're thinking of. This is Murray and Williams that showed that a bunch of reductions cannot prove NP completeness, but you're thinking about something else. Okay, I will look it up and try to see if tomorrow I can actually say something about it. Thank you so much. Okay, more questions, comments about the Levin's notion of KT. So let me fairly briefly mention two more notions of time-bounded Kolmogorov complexity. And I will come back to them, but I just did not want to have too many different things with different behaviors that hard to keep straight. Okay, so here is a different notion, and this one is usually attributed to Kerr-Eco. And maybe in a way, this is the one that you might have come up with first if somebody would give you Kolmogorov complexity and ask to scale it down. But the way it is, you fix T. And then you ask what's the minimum description of a machine that prints, what's the minimum description from which the universal machine prints X in the time that T that you fix. At least this is how people talk about it nowadays. Original definition was you give X, you give a T and S in unary, and you ask for this X is a machine that runs in time at most T and prints, with a description at most S. So T was a unary, S was a unary part of the input, so that solves some of the issues with Levin's log. And now people sometimes kind of talk about it in a more generic way. For example, when you read meta-complexity literature, you will often see K superscript poly, where they just say, well, let's take T be some polynomial time computable function of the input, and we are going to say something about K capital T for this class of T's. And this definition is the one that have seen a lot of attention very recently, because this is a definition that people manage to use to prove connections with cryptography. And this is a definition for which people manage, well, kind of, a version of this is the one for which people manage to prove worst case to average case reductions. Again, lots of sudden, the devil is in the parameters. So on one hand, it was shown by Liu and Pass in a big result 5 years ago that if this problem is hard on average if and only if one-way function exists, which was a big deal because up until then there really was not much of connecting average, well, there was a lot of connecting average case complexity to cryptography, but this wasn't genuine if and only if. One-way functions correspond, I will talk about them probably tomorrow, correspond to a ton of stuff in cryptography. Essentially, they capture the notion of private key cryptography. Public key cryptography is a next world over. But having kind of all of the private key cryptography existing, being equivalent to a hardness of specific meta-complexity problem, even if on average this was a really big and cool result. And what was even more big and cool is that a version of this problem, MKTP, the version in which you are asked to distinguish between there is a small circuit, there is a small description from which you could recover X in time t, or even if you take much bigger S, and if you allow more time, there is nothing. This version for some setting of parameters and for a different definition of what it means to be on average has a worst case to average case reduction. So if only we could like just squeeze those two things together, then it would be a big thing for cryptography, because basing cryptography on worst case hardness of problems is big, is great. That would eliminate a lot of issues with all cryptography can be broken by quantum, with my apologies. And this would be really cool. But devil in the detail, errorless complexity versus complexity where you do allow errors seem to behave differently. Just to say that if you want to know more about it, Han Lin had a recent paper about this, and he could tell you all the gory details. And also, this reduction worst case to average case is the one Rahul Ilanga spent a lot of time explaining last summer at DIMAX. So I won't be explaining it because he did an amazing job covering all the details of it. But just so you know. Questions, comments? Okay. And let me introduce you another animal of the zoo. Again, I'll come to them later. I just wanted to put them on the slide in the first lecture, not because I'm focusing on them, but just to tell you that they exist. There is one more notion of deterministic time-bounded Kolmogorov complexity, and that one is usually attributed to Eric Allender. From what I understand, Allender's goal was to tie Kolmogorov complexity in the Turing machine world to circuit complexity that he is very much interested in. And so far, the results that I mentioned, they don't really have very, very good connection to circuit complexity. For example, Levin's notion of KT, it corresponds to the circuit that have an oracle gate to some complete problem, not very satisfying. So here is how Eric Allender defined it. Rather than requiring a Turing machine to globally output the string, he introduced a kind of local notion of Kolmogorov complexity, where you're asked, given an ice bit, so there is a machine that takes a description and a number I, and you want to print ice bit of the string X in time t, because in this case you're just printing one bit, you don't need to worry about spending time just producing the output. So here you again, so here you probably would need sublinear time to output some of the things. And so you have random access to your D, you have random access to whatever you want. And you are allowed to run in time much less than length of X. So one notational confusion. If you read papers on meta-complexity, you will probably come across mean KT. And you also come across, so mean KT, all letters capital. You also come across M, K, capital T, P, those are different problems. Historically, min KT with all the letters capital was the name, I think, given by Ko to this notion of complexity, the one from the previous slide. Again, they behave quite a bit differently, and it is confusing to have very similar sounding definition talking about different notions, but this is what historically happened. So I will talk much more about circuits in the next talk, or well, I'll probably start now, but just to say how this relates to circuits. You know, if you have a Turing machine running in time t, you could make a circuit, I think, of size t log t that computes this machine, and vice versa. If you have a circuit, you could have a Turing machine that just executes the circuit, but just for a given n. You also need to worry about generating circuits for arbitrary n. So there is this connection. The main difference is, from what I understand, locality. Here you're computing every bit as you would be computing circuit output, kind of separately from the rest of the bits. And because of that, you might be able to spend less time on each individual bit than printing the whole thing. Do you kind of see what I mean? Okay, questions, comments, more issues with the slides? So those three notions of time-bounded complexity are pretty much the only ones I'm going to be saying anything about. But the next thing I will be talking about would be what if we go from Turing machines to circuits and just talk about circuits. For us, especially for those of us who actually work in circuit complexity, this is a very natural notion of a complexity of at least strings of length 2 to the n, and when we consider them as truth tables of Boolean functions. Just one thing about Allender's KT. Morally, it's very much related to circuit size. There are a few results that we generally, results that hold for Allender's KT also hold for MCSP. Generally, they are harder to prove for MCSP, and there are a few cases where we have something for Allender's KT, but we don't have it for MCSP. Okay, questions? So, kind of, yeah. I have 10 minutes, so I don't know how much I can tell you, at least how much I can tell you of stuff that you don't know. Because switching gears and very slowly and carefully, not very carefully, but slowly defining circuits and circuit complexity. So just to say kind of the plan for the next couple of talks, I want to actually talk about complexity of some special variants of min k, various notions of t, p, at least the ones where we know, and maybe say a few words about when things are not known and why, when we have lower bounds, upper bounds. And then I want to talk about connections with learning and connections with cryptography, but those I don't plan to really get into proofs. I might show you constructions and kind of say, well, you know, the actual analysis is easier to understand when you sit down with a paper and work out the parameters, because a lot of them require very careful parameter analysis, not ideal to do on the slides in a tutorial. Some people do. Yeah. Okay, so as some people say, our enemy is a circuit, or our friend is a circuit. Actually, question for people. How many of you have seen AC0 that is constant depth circuit families? Most, but not all. Good. Okay. Circuit, as in Boolean circuit. Okay. So then I'll just kind of say a few things. Circuits, you are given a description of circuits. Generally, you have list of gates, which you name by numbers, and then you have list of generally edges, and also for gates you have what type of gate it is. That's the most standard way to describe a circuit by a string. If you have here, we will not, for now, we will not pay too much attention of whether your AND and ORs can take arbitrary many inputs or just 2 inputs. It's number of gate factor difference. I think generally when people talk about minimum circuit size problems, they mean the number of gates in the circuit. But that doesn't seem to matter enough for people to really make a distinction. I may be mistaken. Please correct me if I am. So number of edges, wires, on a description lengths are another parameters you could think of, but if you think gates, you'd be good. So another part is when you are given a specific string of length 2 to the n and ask what's the circuit for the corresponding function, that makes sense. When you're asking things as a function of n, that becomes murkier. Generally, we'd be talking about circuit families for every size and what is the size of the corresponding of circuit computing a function which has a description that's not tied to a specific number on function on that many inputs. And what makes things interesting is we generally don't require those circuits to be generated in even computably. So there are circuit function families that solve undecidable problems, and it's okay. So do you know this one, the circuit family that solves undecidable problem? Okay, here is my undecidable problem. For x, I ask whether Turing machine number length of x holds on blank. Undecidable? How do I solve it with circuit? Well, for every number x, I either put a circuit that's constant true or the circuit that's constant false. Because for every number x, well, there will be only one machine. And it either holds or doesn't. This is the power of circuit family. This is one reason why things like what Bruno was mentioning, that it's unbelievable but not unproven that all of exponential time can have a polynomial size circuit. This is still up in the air. Even though we know that deterministic machines in polynomial time cannot compute exponential time complete problems. Okay, MCSP, you're given a function as a truth table string of length 2 to the n. You're asking what the circuit size. Generally, sometimes for some function families, it may be constant independent on how many inputs it has. Like, oh yeah, I just output my last bit and this is my answer. For some of them, we do have lower bounds, at least for well, we do have lower bounds for small classes. And what we do know is that just like in Kolmogorov complexity, vast majority of functions will need circuits of nearly maximal size. This was shown way back in 1949 by Shannon, and it's just a counting argument. There are fewer circuits than there are functions. But very embarrassingly, for a problem in NP, the best bound we know is something like 3.1 times n. And this one was like a pretty big breakthrough. Okay. So I guess I'm standing between you and lunch. So let me just say that there is a reasonable definition of minimum circuit size problem, just like there is for all the other measures. And a question that bugged a lot of people for a lot of years is how hard is it? You're given truth table. Is it polynomial time? Is it NP complete? Is it intermediate? We know that there are problems between P and NP if they are different. They're not constraint satisfaction problem, but neither is MCSP. Okay, so let me probably finish this slide, and I'll continue talking about complexity of MCSP and friends tomorrow morning. Any questions, any comments, any corrections?
What are the questions that show that MCSP doesn't give any lower bounds?
You're like 2 slides ahead of me, or 1 slide? Yeah, so it's again very much hinges of what kind of reductions you could do, but under the kind of reductions that we usually have, if MCSP is in polytime, then at the very least you get circuit lower bounds. Sometimes believable lower bounds, but you do get circuit lower bounds. And also, if MCSP is in polytime, then saying it loosely, cryptography disappears almost by default, because you could always tell whether something is an output of a one-way function, which is a polynomial time computable with a small description, or something completely random. And as soon as you could distinguish random from something produced by a small size object, cryptography goes out the window. So yes, thank you. Oh, did you mean something else?
No.
Yeah. Okay. Question, comments, or lunch? Yes. Oh, sorry.
Also true for KT, right? I guess.
I think so. Yeah. Okay. For which? Yeah.
Okay.
Yeah. For at least the Allender's KT for sure.
Okay.
For cos KT, we do have an NP hardness result.